All right, so to get started on 1.3, hopefully you've already answered question 1. We're looking at Scott doing these push-ups, right? And if we're looking at each individual day, we should kind of notice here that, hey, this has 2 more than the next day, and each day he's adding 2 more push-ups, right? So if he's adding 2 more push-ups each time, right, we could see that as an arithmetic or a linear sequence. So therefore, if we want to model in both the explicit and recursive form, for our explicit, we can think about it as f of n or f of x. It doesn't necessarily matter what variable you use, but our initial value is there's 3 push-ups on that first day, and he's adding 2, right? And then we've got that n minus 1, right, to accommodate that we started at 1 and not 0. Or an equivalent format there is just 2n plus 1. Which you may see, another way to kind of to visualize this is, hey, down here at the bottom, we have twice the number of days there is, right? So here we've got 2, we got 4 at 2, we got 6 at 3, we've got 8 at 4, and there's 1 extra. It's another way to visualize it. Okay, so with that in mind, actually I'm going to write that in purple so you kind of see where they connect. So this is the 2n plus 1, if you want to do it that way. The last thing is they have the recursive formula. So the recursive, so this is your explicit. Remember the recursive is talking about, okay, what do we start with? So on day 1, we have 3 push-ups. And then you can choose to use f of n or f of x. It doesn't matter, but your homework has used x, so I'm using x here. And we take the f of x minus 1. Remember, this just indicates, hey, the previous term. Right, so like what happens, we're talking about day 2, we take the 3 push-ups from day 1, and what are we doing with that? Well, here we are adding 2 more. So those are the 2 equations. You should have come up with number 1. Okay, at this stage, pause the video, read the next part, and then we'll jump into looking at 2 through 5. So, as we take a look now, and we're looking at the total, this first one, notice it says to estimate. So really, it's up to you, right? Use your estimation skills. I hope you guessed more than, 9, because we saw 9 on just day 4, but how many would he have done in a month? Okay, and then we want a diagram that shows the total number of push-ups he's done. So one way to think about it, on day 1, right, he's only done those 3. 1, 2, 3. But on day 2, he's done that original 3, right? But then he has done 2 more. So this is the way I thought about drawing the diagram. Not to say it's the only way to do it. And on day 3, he had that, what we already have, right? The original 3. And then he's got the 5 for the next day. And then we got 2 more, so we got 7 for the day after that. Okay, and then on day 4, you could think about, okay, we got our day 3. We got our day 2. We've got our day 3, I'm drawing that still. So we got all this, one more column for day 3. And he's got 1 more on top of that, right? Sorry, this is not very equal, but we get the idea. We do not expect you to be perfect artists. This is math class after all. And it helped me just to kind of label these a little bit to kind of see what was happening. Like, I noticed here, right, that he's got on the day, so like we can say the day, and then we can say the total. He's got on day 1, he's got 3 push-ups, and on day 2, he has 8, and on day 3, he's got 15, and on day 4, he's got 24. All right, so here, right, you're adding the 5, you're adding the original, I guess I won't talk about the adding right now, sorry, take that back. So we've got our diagram. Okay, so now we say how many push-ups we have done after a week. So there's a couple ways you could do it. You could start to kind of think about an equation at this stage, or maybe you just continue the pattern, you continue your table. But the correct answer here, and there's more than one way you could have done it, is 63. So I hope you got that. If not, let's take a look at the equations in a second here and see if we can see how kind of some of these things worked out. So for our different equations, one way you could look at it, right, I think the recursive's a little easier. Okay, so if we say on our first day, we're starting with 3. And then on our next day, so whether you do f of x or f of n, we start with the day we had previous, how many we had previous, and then we're adding some number. So this is where I find it easier to kind of look at. So like to get to day 2, I'm adding 5. To get to day 3, I'm adding 7. To get to day 4, I'm adding 9. So like to get to day 5, I would add 11. I get 35, right? So we can see that pattern. So you want to associate the 5 with the number 2, the 7 with the number 3, the 9 with the number 4, the 11 with the number 5. So how do we associate that? The way that I see it is I see that as the 2x plus 1. It's double that number and 1 more. And kind of a cool connection here is if you look at this, notice here we have plus 2, plus 2, plus 2. So we see that that second difference is the slope in that linear you're adding on. So remember when we add a linear to our previous, that's what we get as a quadratic. It has a constant or common second difference. Okay, so now let's go ahead and look at some different equations. There's definitely more than one way you could look at this, right? So one way you could look at it is you could rearrange it, right? So I kind of thought about rearranging it into squares. So if I think about rearranging these into squares, I'm going to, actually it becomes a rectangle, but if I look at like the second one, I'm going to take every other row and rearrange it. So I'm going to actually, yeah, I can do that. So I can take every other row and rearrange it. So I'm going to take these, notice, like every other row, and I will make a square out of that. Okay, so if I do that, actually, sorry, I apologize, a rectangle is what it makes. But like notice on that first one, I'll redraw it over here. But on that 2, you could get, okay, so I'd still have that bottom row, right? And I have those bottom 2 rows that haven't changed. And that third row, I'm going to kind of flip on its side. So you could almost say that third row, I'm going to actually kind of flip it around and take these 2 parts. And so this is the original, and then in the ones I shaded in, I'm going to flip it such that it kind of completes that. So now on that second one, it's making 2 by 4. Okay, and then on this next one, if I do the same thing, so I still have it's 3 on the bottom, and I can keep those bottom kind of 3 rows, bottom 2 rows, and then I have a 2, and then I have a 1. So then this is where you start kind of flipping it. This is what I'm imagining, this part that shades in, and 1 more. So here I now have a 1, 2, 3, a 3 by 5. And I could continue that on. So what I'm noticing here for f of x, my explicit one, right? I have on that second one, I have just x, but then on that next one, I have that x plus 2. Okay? Not the only way to think about it, so sorry if that wasn't the best explanation. If you wanted to think about it a different way, another way you could kind of see it is taking like a square, so like kind of looking just at this top part, if you rearrange it, and seeing, okay, hey, this part, right, is a rectangle, and then we got 2 extras, right? We got this rectangle on top, we got 2 extras, and that one would look more like f of x equals x times x plus 1, but then notice on the bottom there, again, we have an extra, just 1 along, but at the size just x, so an extra x, right? There's lots of different ones. Another one that does end up being equal is like f of x equals x plus 1 squared minus x. These are all end up being the same equation. Remember, the cool thing about tasks, there's lots of ways to look at it. So, great. We kind of know how to come up with these quadratics. We understand kind of where they're forming. We can see that common second difference. And let's talk about these quadratics, right? These explicit equations we come up with are quadratics. In particular, I want to look at how we multiply these. So how can I see those equations we wrote over there on the right are all equal? So I'm just going to look at x times x plus 2. This one you probably already know. You just distribute it through, right? So we had some of that in our practice. We'd have x squared plus 2x. That's not too bad. We can see that. Okay. So now let's look at the next one. This one we have x times x plus 1 plus x. So let's think about it. Let's distribute again. We get x squared plus x, right? Combine your like terms. So once again, we get x squared plus 2x. Okay, this last one's maybe a little bit trickier. Here we've got x plus 1 squared minus x. I'm going to have us rewrite this because this x plus 1 squared, you may be tempted to kind of distribute through, but it's really x plus 1 times x plus 1 minus x. And we'll spend some more time in our next unit working on that, so I will not stress a ton, but it will come. But here, notice, we rewrote it in our homework, right? So we took the x and we distributed that x to that whole x plus 1 on the end. And we took this 1, we're going to distribute it there as well. So we also had the plus 1 times the x plus 1. And this is what your homework looked like, right? And now we can distribute it, and it's like those first two examples. We get x squared plus x, distribute the 1, we'd have an x plus 1, and we have minus, oh sorry, I miswrote that equation up there. And since this is just a video, you cannot stop me. This should have been a minus 1. I totally apologize, minus 1. So then when we subtract 1, we look at it, we get x squared, we get 2x, and the 1 minus 1 cancels. So they are all equivalent. So I feel like there's two ways we can look at multiplying. You can think about distributing just like we did there. So we can take the x out front, right? So we can take it, look at this x and distribute it to this x plus 7. So x times x minus 7. And I can take the 5 and do the same thing. So I've got my plus 5 and distribute it to x minus 7. So I'd have x squared minus 7x plus 5x minus 35. And then I can combine it. I get x squared minus 2x minus 35. Something that I kind of like, so you can totally think about a distribution that would work the same way over here. And we'll kind of get to this as well, but I kind of like actually drawing a box, and you'll kind of see the need for this as time goes on too. But it just helps keep me organized. If I do my 3x minus 5, and I do my negative 2x plus 1 on the other side, I can then think about it the same way that we can then distribute. So like we're really taking the 3x, distributing to both parts, but I'm multiplying this in this box format. So 3 times negative 2 is a negative 6. X times x is x squared. 3x times 1 is just 3x. So I distributed that 3x to both parts. Same with a negative 5. Negative 5 times negative 2x is positive 10x. 1 times negative 5 is negative 5. So now if I rewrite this, negative 6x squared plus a positive 10x plus a 3x minus 5, I end up with negative 6x squared plus 13x minus 5. Doesn't matter to me which format you like, choose the one that works better for you. Okay, got two more examples to look at. We want to look at the first and then the second differences to identify as linear, quadratic, or neither, and then write some equations. So here, we will notice, okay, we're adding 2, oh sorry, it's not adding, we're subtracting 2. And it looks like that's happening all the way through. So if there's a common first difference, we know that it is linear. Okay, so our recursive equation, I always like starting at f of 1, but here technically it does start at negative 3. You could do f of negative 3 equals 24, but since our format's usually f of 1, let's do f of 1 equals 16. And f of x equals f of x minus 1, and each time we're subtracting 2. Okay, as we take a look here, we're just seeing what the difference is. So we are subtracting 16, and then we've got another 16, and then we've got 6, and then we've got a positive 4 a positive 12, and a positive 24. And I apologize, that's not 12, that's 14. So now as we look at the second difference here, this one, sorry, this was a 26, we got adding 10. To get from negative 16 to negative 6, we add 10. To get from negative 6 to 4, we're adding 10 each time. So since this second difference is consistent, we know that this is a quadratic. Okay, so we need two things for our recursive equation. We need f of 1, which is, in this case, 4. Or you could do f of negative 3 is 48. And then f of x, or f of n, equals f of x minus 1. And then in this case, we're adding something linear. That second difference, which is 10, is going to be the slope of it. So we're going to have a 10x. And then we just got to figure out, well, how do I adjust that, right? So in this case, we are adjusting it negative 6. And the way that we're getting that is, like, if I just try, let's plug it in. So if I did, like, f of 2, right? I'm going to take the first term, which is 4. And if I add 10 times 2, I notice I get 4 plus 20. And I get 24, but I really want it to be 18. So I need to take away 6 from that. That's the way I like to think about it. Up to you if you want to think about it another way. Moving on. So let's take a look at the next one. The last one just says write the first 5 terms of the sequence. So can we read equations rather than write them? So this first term, right, f of 1 means the first term is just negative 5. And then what is this saying over here? It's saying to get to the next term, we take the one that comes before it, and we're adding 8 each time. So if I add 8 to negative 5, I get to 3. I add 8 to 3, and I get to 11. I add 8 again, I get to 19, and then I get to 27. All right, good luck with your assignment.